And we are back for our PSET 5 solution video. So let's go ahead and get started with a lot of beam bending problems. So let's go ahead and just ignore the cantilever beam test. But we can rename this as number 1. So I'm looking at the following scenario for a PMMA beam. So I know that my Young's modulus is equal to 1 times 10 to the 9th. I also know that I have a beam that the length of my beam is going to be equal to 5,000 centimeters times 10 to the minus 2. I know that I have a thickness or a height equal to 7 times 10 to the minus 2, and then I have a basically a base that is 15 times 10 to the minus 2 here. Excellent. So we've got those values here. I also know that I have my rectangular cross-sectional area is base times height cubed divided by 12. We've got that value here. Base times height cubed over 12. So I've got my I, and we're getting ready to go. Excellent. So looking at the loading scenario, what do we have here? Well, I do have some load that's placed at L over 5, a point load, so a Dirac delta function. The value is going to be 70 kilonewtons. It's pointing in the down direction, so minus 70 times 10 to the 3. I'm also having another point load. So I'm going to do minus. That is 80 kilonewtons. So 80 right there. And it is at L, basically at 3L over 4 here. And then I also have a distributed load across the whole thing, 50 times 10 to the 3. So that is essentially my function. And here, let's go ahead and move it over here now. So this is my function. I'm going to zoom in just a little bit. Our general expression that we've kind of been using quite a few times in class. So we also have essentially these supports here. So I know at these supports, I am going to have no deflection here, but I'm also going to have no restoring moment there as well. So I can set my boundary conditions as follows. So at y of 0 equals 0, at y of L, so the displacement is equal to 0, and then y double prime of L is equal to 0, and also my y double prime at 0 is at 0 should be equal to 0 as well. So those are my 4 boundary conditions. We've got that there. I'm going to get rid of essentially this assumptions page here. Give me my dsolve. So this is going to be my, I'm going to call this my displacement is equal to this. And I can look at my displacement here. And we can see essentially, see those values here. So we've got our displacement. So if we want to find what is our maximum displacement, for example, we can go ahead and start to solve for all those values here. So we can actually, 0 to 1. So you see that's the problem here. Let's plot from 0 to L. There we go. That looks much better. I was getting a little bit nervous. Excellent. So I could find minimum. So if I want to find my maximum displacement, find minimum of displacement for x, and I can see where that's located and the actual value here. Quite a lot of displacement because it's a value. So I needed the expression for displacement, shear moment, and bending moment. So let's go ahead and find my moment equals minus y times I times the derivative of displacement x to the squared. I also have that same expression holds for my shear, minus y times I displacement to the third as such. And we can now plot, actually, let's just get rid of all of this stuff. So I'm going to plot my shear from x from 0 to L. So I can see that right there. I'm also going to plot my moment from x from 0 to L. And we've got those values as well. So location of maximum displacement and the value, we've already got that. Shear moment, we can find that as well. So find maximum of shear with respect to x. And let's give it some bounds. So sometimes you need to effectively give these expressions some bounds. So I think we have to go from, and I wish we could do, we should get some help. Find minimum. And then we can actually see, let's contain this effectively. So I want my, something like this. And we'll utilize this for a little bit. So I want my function, which here is going to be shear, and I want it from greater than or equal to 0, and then L. And I don't need to really start it unless I need to kind of get those values out. So that would be my minimum. I could also find my maximum value as well. Oops, let's go ahead and type that here. There we go. That's nice. Excellent. So I've got my maximum, got my minimum. I can do the same thing, actually, because I know I'm going to need my minimum here for my bending moment. Right there. And now I can start to, my stress is going to be equal to minus my moment, the maximum of my moment, times my height over 2, my y, all divided by I. Actually, let's divide this whole thing, divided by I. So this is where we want to kind of take a pause for a second here. And actually, it is a little bit of a significant issue that can occur. If I'm bending, and if I look, and actually if I plug in, let's just plug in this value of maximum, or that minimum effectively moment here. What is my stress at the top of my beam? Because this y is positive h over 2. It's saying that that stress should be in tension. So sometimes the definition from that we use for our moment is different from what we define as positive or negative bending moment. So we'll have to flip that sign. So it's just something that's hopefully a little bit straightforward, essentially, of how we actually deduce that. So we can now go ahead and move further with the problem. All right, so I got the stress there, and if you want the basically negative compression stress there as well.